Hello everyone. So today's video we will be focusing about how to design the basic logic gates on the Shrike-Lite Development Board. In this video we will be designing the AND gate, OR gate and NOT gate. So let's get started. First of all, we will be designing our logic gates for the simulation purpose. Thereafter we will be focusing on the development board. So let's start for the simulation purpose. Let's name our module as logic gate. Let me first save this file. Let's rename it to. Okay, so we have two input A and B, and within the same module we will be doing all the three outputs, that is output and output or output not output. For the simulation purpose and also for the FPGA development purpose, we will be following the data flow methodology or the data flow process of writing the Verilog code, that is using assign statements. So here we have finished our module, and as we can see, like we have written assign using the assign statement. What actually happens in this data flow model is that as soon as a signal on the right hand side of this equals to that is A and B, or A slash A or B, whatever written on the right hand side of this assign operation, if any of the signal changes, instantly it will change and reflect the result on the left hand side. It's just like being connected using a continuous wire. So as we have finished our logic gate, let's just write the test bench for it also. Let's define our time scale, that is 1 nanosecond with a resolution of 1 picosecond. First of all, let's save our file. It will be named as logic gate underscore tv.v. Okay. Just like in object-oriented programming languages, in this case also we have to initialize our, or sorry, we have to instantiate our module. The module that we are going to test is this module, logic gates module. So for that we have to instantiate it. Let's instantiate logic gate. DUT refers to design under test. It is a common practice. Here we have connected all the signals here, like dot A. Here the dot A refers to this signal, to this A, this B, whatever we are writing here. This is this part, and we are latching it up with these variables. What does that mean? That means like whatever input we will be providing in our test bench to this A, B, that will be reflected out to this A and this B, which is actually nothing but these inputs. And whatever output we generate from that, that will be actually latched out to our or not and O, which are mentioned here. So let's start. Initial begin. Initial, it is a procedural block. It only acts once when called. Let's create the dump file. We will not be creating any kind of like any kind of variables or any kind of result that we will be displaying on the terminal. Rather, we will simply be seeing the waveforms. For that reason only, we have written the dump file and dump values portion. Now let's assign the values A0, B equals 0, hash 5. So see, we have mentioned all the 4 combinations that are possible with using the 2 bits. Now, what does this hash 5 means? It means a 5-unit time delay after every signal. Let's finish our simulation. End module. So we have written both our logic gate module and the logic gate test bench. Now we will be focusing on how to run this part. So as we can see from the timing diagrams, see when A and B both are 0, not except not everything is 0, and that is supposed to happen because not for our logic we have written not as negation of A. So as long as A remains 0, not will always remain 1. As soon as B changes to 1, we have OR equals to 1, not remains 1, As soon as A changes to 1, we get not equals to 0 and or equals to 1. And finally, when A and B both are 1, we can see both and or are 1, whereas the not signal remains 0, which is, so this actually justifies our module description and the modules that we have written. Now we will be focusing on how to write this exact code for our FPGA. Let's close this. Here, this software, this is known as the Go Configure Software Hub. This is actually provided by Renesas company, the same company that provides us with the FPGA on our Shrike-Lite Development Board. So let's just search our part, that is the ref bb part. This is actually the FPGA we are connected, like we are targeting. Let's rename our file as and get. Let's select a folder and get. Wait a bit. Yes, we have the project settings. For the project settings, for this pop-up, just select the first value that we get on clicking the upper arrow. These are the optimal values that we need to set, then hit on apply, then OK. So here we have our FPGA core. But before going into this FPGA core, one thing I would like to say, like, let's just focus on to any of the GPIO. See GPIO 14. We have in out OE external in slash out. What does this configuration means? For this Renesas FPGA, we can treat every GPIO as either an input pin or an output pin. What actually happens is, when we are trying to use a particular GPIO as an output pin, we need to set this OE signal. As you can see here, it is written OE, this signal, as 1. Until and unless we set this signal OE as 1, the GPIO will not act as an output pin. This is one of the features of the Renesas FPGA. So for our purpose, let's just click on this FPGA core, double click. We have the main.v. As we have seen earlier in the video, we have written the code for all the logic gates using traditional Verilog method, traditional Verilog style. However, for the FPGA development, there are certain parameters that we need to pass, or certain style that we need to follow. One such style is this star top star. This actually signifies the module that we are writing that should be treated as the top level module, and accordingly the synthesizer will synthesize the entire design. So let's rename our file as and get. Here again we have to mention a certain parameter part, IO pad external pin. As we are going to use the GPIO, so we have to mention this IO pad external pin. Output we have, let's suppose C, right? Now let me just copy it. Again we have output C enable. Then we have input A. Then we have, let's just zoom in a bit. Yes. Then we have input B. Now again, following the data flow model, we will write assign C equals, as we are creating only the AND gate, A and B. So our module is finished. Let's save it and click on synthesize button. See, here we have obtained 3 warnings. One of the warning is like expected, that is the network is purely combinational, that is an warning, and another that wire and gate C enable or CN is used but has no driver, as a result exporting X bit on C enable as 0 bit. See, we have mentioned this output. However, we are not using this output or latching this output to anything. That is why we are getting this warning. However, as we discussed, to get this output C, we need an enable output enable pin, and that is nothing but the C enable. And as I said earlier, we need this to be 1 in order to get the output as C. So let's just mention assign C enable equals 1B1. Again, let's save the file. Again, click on synthesize. See, we actually obtained only the network is combinational thing, nothing else. Now we need to go to the IO planner. See, for every GPIO pin here, we can see there are 3 options: out, out enable, and in. This is same for every GPIO pin that is actually available on the FPGA. So we will be following GPIO 0 and 1 as our input. GPIO 0 input, that will be providing us with the input A. GPIO 1 input, that will be providing us with B, and GPIO 2, let's see, GPIO 2, that will be providing us with the output. GPIO 2 is actually the output. GPIO 2 output enable with C enable, right? Let's just save it, save all. Now we need to click on the generate bit stream. Again, click on yes. Okay, so here we can see the report. Let's click on the synthesis report. This is actually the synthesized report that is actually being used. Here also you can see the resource report. The resource report here, the RTL input ports, RTL output ports. Though keep in mind, though the enable output is actually not being an output, but we have mentioned that as a output, RTL output in our RTL code. That is why it is showing RTL output ports equals to 2. GPIOs, we are actually using 3 out of the 19 available, that is the 2 inputs and the 1 output. Here we are not considering the output enable, because output enable itself is just a signal, it is not actually an output. And all the warnings that we get here, that is the user IO IBUF is not, this may cause potential interface timing issues. This is just because we are creating a combinational circuit, that is why we are getting this kind of error. Not an error, but a warning. We can successfully ignore this. So let's just here you can see the netlist that is being generated by the synthesizer, that is EOSys, the entire netlist. Now let's see the floor plan. If we zoom in, we can see we are actually using a single CLB. A single CLB is being used, out of which we are using all these GPIOs, GPIO 2s, in, out. So these are the GPIOs we are using. It is the floor plan is designed. So we will be designing we have designed the AND gate. Now we will be designing OR gate and NOT gate also. Then we will be moving towards the FPGA deployment. So we have successfully created all the 3 parts, that is all the 3 logic gates for our FPGA. Now we will be going towards how to upload the code into the FPGA and how to actually test the FPGA. So after developing our code for the FPGA, we are going to upload the code into the FPGA, and to do that we need the Thonny IDE. We have connected our Shrike-Lite Development Board with the computer using an USB cable. Here we can see this MicroPython. We will select this one. This is RP2040 dev TTYSEM0. For your computer this might be different based on the COM port. So for that, to let the FPGA basically work according to our design, we first need to store the binary file that we have generated from the Go configure software, that we can see here, and get double FPGA build bitstream. Be careful, we need to upload this one, FPGA bitstream mcu.bin. We will upload this. You can rename it also, I have not done that. We will upload this into the RP2040 device, and then we need to write this main.python file. Do remember, this main.python file, this will be responsible for flashing the binary file into the FPGA. This is being done using the RP2040 microcontroller, which is also present on the same development board. We will just write import shrike.flash, and the bits binary file that is needed to be flashed into the FPGA. After that, once we click on run script, FPGA reset done, starting FPGA flash, flashing the bit stream, FPGA programming done. Once this programming is done, now we will be verifying using the real-time signal on our FPGA. Just like the AND gate, now we will be doing the for the OR gate. I will just replace the bit stream file, that is the binary file that is currently present in the RP20 device, with the binary file of the OR gate. Upload. It's basically overwriting the binary files. As I have not named them differently, so it's okay. Now main.py I will run. It's flashing. The flashing is done. So we will again be seeing the FPGA performing OR operation in real time with real time signals. Same process, just like AND gate and OR gate, we will do for the NOR gate.